Hi, everyone, and welcome to the next session. We have Antoine Jacquier. He's a reader in mathematics and director of the Master of Science in Mathematics in Finance and visiting researcher at the Imperial College in London and the Alan Turing Institute. And Antoine Jacquier is going to talk about solving financial equations using quantum computing. Exciting. Thanks, Antoine. The floor is yours.
Right, so thank you very much, and thank you for the invitation. So just to make sure you can hear me well and you can see the slides, right? Just to make sure that this will work.
All good.
Perfect. So I have to apologize in advance because I'm neither a physicist nor do I speak Spanish. So I guess the intersection is I'm one of the few who don't match any of the two criteria today. But nevertheless, so what I want to, maybe I should say a little bit before starting the talk. So as you can see, the main title has changed a little bit, which is QF or QF. So the first QF, as you see, is a funny calligraph, I don't know, some kind of particular font, and this Q stands for quantum. So the first one is quantum finance, and the second one is quantitative finance. And so my background is, so I'm in a math department in Imperial College, and I come from mainly stochastic analysis, probability, and mathematical finance. So I've been working in this field for quite a few years now. And so that combines stochastic analysis, probability, numerical analysis as well. And I have virtually no background in physics, no background in quantum mechanics, but I view myself as an applied mathematician, meaning that I'm actually interested in interesting tools to solve interesting problems, most of them related to quantitative finance. So I've started dabbling around a bit with quantum computing over the past 2 years, and so this is one thing we did recently. But I want to take the opportunity in this talk actually to start with a few slides about why do we or should we or may we need quantum computing in quantitative finance. And so when I say quantitative finance, I mean both from the academic side, so on the theoretical side, and also from the practical point of view, and looking at several problems that are of extreme importance in quant finance. So I will very quickly, because that's not the core of the talk, but very quickly show you 3 or 4 topics that are of primal importance in quantitative finance, and where quantum computing actually can bring something, in my view, but there's already been a few works on that, but I think there's a lot to be done. And then switch to the thing we actually did recently. So the first thing is, if you look at time series data, so this is SPLAC. So SPLAC 40, you probably know better than I do. It's a major index for equities in South America, which represents basically the largest 40 companies from all the countries in South America. And so this is over the period, I don't know if you can see well, 2011 until now. So the top left is the actual index, and the right are the returns, the one-day returns, right? So as you can see, if I want to be able to understand that behavior and to build a model to understand that behavior, I can't have any model that is deterministic, because as you can see, even if I just look at the returns on the top right, they're very wiggly, right? They're very uncertain. There's a lot of noise in the data. And so standard type of models that we use in quantitative finance. So I apologize in advance for those of you who know about quantum finance a bit already. Those might sound standard, but just so that we have a common bag of words and to discuss. So the typical tools we're using is stochastic modeling, where so S is my stock price at time t, and as you can see, the return, so that's dst over st, right? So that's the short period. So dst, you can view it as st. I can actually do this. dst is st plus delta minus st. Right, so that's my dst over st, so that's the return. I have a drift, maybe something linear, and some noise, right? And w is a Brownian motion, which basically is some noise that allows me to model this kind of noisy dynamics. How do we model this? So, for example, I took mu and sigma that are estimated over 20 days, and the plot below is just one simulation, right? So I have to admit and confess, I did it a few times to get something that looks a bit like the top right corner, but the bottom one is really simulated data. Of course, I did that quickly, so I was not aiming at getting something very precise, but it's just that intuitively, visually, those are kind of sensible ways of modeling the dynamics, because as you can see, they have similar shapes, similar characteristics. Okay, so that's the first tool we use. And of course, if I want to be able to compute things, I need to be able to simulate those processes. And simulation is difficult in general. I'll come back to it a bit later. And of course, there are promises of quantum computing that are able to speed up computations. There are results, but speeding up those kind of simulations using quantum computers, those are still theoretical for now. But we are looking for better, for new algorithms, maybe from quantum computing, that allows us to do that better. And when I say better, I mean faster or more accurately. The second problem is option pricing. And this is key because those are financial derivatives that are traded all the times and very liquidly on markets. And I'll just show you some very quick examples. So S is the stock price, right? But when I write bold S, this means the whole dynamics, right? So this is ST when t evolves between, let's say, today times 0 and some maturity, capital T, so 1 year. And what we are interested in is to compute the expected value of some function of S. So the classical examples that are available in finance are call options, where I'm just computing at maturity capital T the max of ST minus K, where K is called the strike, but it's written in the contract, and 0. So you have call options, put options, which are very standard, extremely liquid, but you also have options that the only reason I wrote those two is to emphasize that those depend on the whole path of S between 0 and T, and not just on the terminal time. How do we price those? Classically, so when I say classically, I mean not quantumly. It's essentially doing Monte Carlo simulations, or as we'll see a bit later, using PDEs whenever possible. There are some issues, in particular, as soon as you have high dimensions, because this is for a single asset, but you could have many assets. This becomes hard. And when I say hard, I mean from a PDE side, basically impossible, or from the Monte Carlo, from the simulation side, it's becoming extremely computer intensive. So there have been some recent advances from quantum computing, so to encode these distributions, because of course S is random, right? So if I look at S capital T, this has a certain distribution. If I want to compute it in a quantum way, then I need to encode this continuous distribution into a quantum state. So this might ping a little bit from the first talk, where how to encode continuous distribution into quantum states. There's also quantum Monte Carlo, but for path, there has not been much so far. So I have to apologize again for one thing. I'm not listing many references on the slides just because there have been quite a few in the past few years, and I don't want to overload the slides with references, but I'm very happy, of course, later on if you need any more detailed references to provide them. Option pricing is one. Portfolio optimization is an extremely important one, which is, so suppose you have n assets, right? So n can be as large or as small as you wish, and you want to invest in all these assets, right? So you invest in asset S1, S2, and so on, and with some weight alpha I. So all the alphas between 0 and 1, for example. And what you want to do is you want to have the best portfolio possible. What it means is you want to minimize the variance of the portfolio. So think of it as a risk. So you want to minimize the risk. Subject to what? Subject by your target, the expectation of the portfolio, being larger than some target. And some target mu star, which is what you tell the investors that the portfolio will return over a certain period. But then you can have a certain number of constraints. You can have that the weights of your portfolio of each asset have to be between a lower value and an upper value, because, for example, you have to diversify, so you can't invest everything in one asset, but you can have loads of other constraints which are dictated either by the market or by investors and so on. So in a way, I mean, not in a way, but this is just a large dimensional optimization problem. Large dimensional because n, the number of assets, can be very large. When I say very large, it can be 200, 300, for example. It's not easy to solve because in general this is not a convex problem because of all the constraints. So there are ways of solving those problems, but they're slow. But there has been quite some interesting results and advances recently, actually, because optimization problem, there are some very natural links with easing problems, so that you can write the solution, the optimization problem, as a solution to what basically as the some eigenstate of some Hamiltonian, right? And so quantum annealing, for example, which I don't want to enter into that debate, which some may say, oh, this is not really quantum computing, but it's in, let's say, the quantum bubble, or under the quantum umbrella. Quantum annealing provides ways of solving that kind of problems. I should mention in passing, this is something I've actually been discussing recently over the past few months with some people at Quantum South. So there are some extremely interesting problems there, how to solve these problems, how to also on the theoretical level, how to prove convergence, what kind of size, what kind of dimension we can solve, we can hope for, and so on. And the last example I want to talk about, and then I'll go into the core of the topic, is machine learning. So in quantitative finance, this is a huge area now, which it has been there for a long time, but there's been a massive push towards it in the past 5 years, and now it's becoming more and more important. So the first one is neural networks. So it seems, when you look a bit at the literature and talks, it seems there's neural networks for everything. Are they actually good and efficient and accurate? That's a very different debate. There are positive things about them. There are loads of uncertainty, so we need to work actually more on it to understand them more. But of course, there have also been ways of writing quantum versions of these neural networks. One thing I want to mention, for example, is the way they're used for data generation, and this is extremely important because if you think again of this SPLAC example, right? So this South American index of equities, I only have one time series, right? Every day or every minute, depending on the frequency, I observe a value for the index. Now, if I want to try and not replicate, but mimic the index, or try to build some risk estimation, maybe what I want to do is generate many scenarios that will tell me, okay, I'll observe the past year and I'm going to simulate it for the next 6 months, and I will have many samples, and from this I can draw some conclusions or some estimation and so on. But if I want to do this, I need more than one time series, because one series is just one example. In physics or in chemistry or in biology, you can rerun the experiment many times, so you get a lot of samples. So one way is this generative adversarial network, which are basically ways of mimicking data. So I wrote fake, but I don't like the word fake data so much, that's why I put quotes, but mimicking data, right? Generating data, generating lookalike data. And I think that's where actually quantum computing, there are some very interesting works actually by, for example, Alexei Kondratyev in Standard Chartered in London, who has been working on a quantum version of these generative adversarial networks to improve them, especially using restricted Boltzmann machines. And these are, well, I was about to say popular, not popular yet, but extremely promising. Right, so I don't want to go too much more into details about this, but this was just to highlight some extremely important areas where quantum computing has seen a few interesting applications, but I think there's a lot more to be done, especially in interdisciplinarity there. Okay, so the one thing I want to talk about, I don't want to spend too much time, but I'll still walk with you through the details. So I want to price option. It's a European call option, which is the standard option we can think of, right? So, which is this. So at maturity, capital T, I have an underlying stock price, let's say this SPLAC index, and capital T is next year. And the payoff is ST minus K, and the max of this and 0. And how do I price? Well, I need to compute the expectation today. And S has some has its own dynamics, right? Which I can run by Monte Carlo, for example. Right. So I want to compute this expectation here, and this thing is the discounting, but you can ignore it for now. It turns out, so I could do Monte Carlo, but actually there's another way, is using PDEs, because it turns out that we know this famous result by Feynman and Katz that tells us that the solution to this problem, which I call V, so V is the price at time little t, and when the stock price is equal to S at time little t, is a solution to a PDE, right? So it's a linear, so it's PDE, right? So I have some DT terms, some DS term, and some DSS term. But if you change variables a little bit, you can directly transform this into the standard heat equation, which is nice because that we know a lot more about it. And you can actually do the same for other kind of options, which I'm going to skip for now. But I'm going to concentrate on basically this heat equation. So I know how to solve it numerically, or actually even in closed form, but numerically using classical finite differences. But what we want to do here is to try and use quantum computing. So the first step is to turn this heat equation, this heat PDE, right, in time and in space, into a Schrödinger equation. And the standard way of doing it is you basically just map time, tau, into an imaginary quantity by big rotation, right? So psi is minus I tau, meaning that your heat equation turns into a Schrödinger equation. And now what my price was, U, then my price function now becomes I view it as the quantum state psi. Right? So psi really describes the price at each time. And so that one we can actually write down the solution explicitly, which is like this, right? Where H hat is your Hamiltonian. And let's forget about this part. Okay, so how do we solve this? So the idea is to use a hybrid of quantum and classical. So the idea is, okay, let me look at it this way, right? So I start from an initial state, and this initial state is basically what I have at maturity, right? So depending on all the possible values of the stock price, this is S minus K positive part. But now at each time tau, between the maturity and now, this is the solution to the problem. And so what we do is we're going to approximate it by, one could say a network, but in fact by a projection onto a space of smaller dimension, which is basically this element here, right? So psi at time tau, I'm going to approximate it by essentially this quantity, right? So psi of tau is approximated by phi of theta, where theta is just a vector of parameters. And phi, so my state phi now is just my initial state psi naught, and I apply, and phi is basically what is just a sequence of unitary gates, but all the gates parameterized by some parameter theta. Right, so essentially I'm approximating my quantum state by a quantum circuit with a certain number of parameterized gates and parameterized by some parameter theta. So starting from the maturity, because at maturity you know what you have, you calibrate it. So calibrating means what? It means I find the optimal vector of parameter theta such that the difference between my quantum circuit and my initial state is minimized. Once I have this, then I can actually solve the running time and solve the problem by discretizing time. So I start from time 0. I have my parameterized quantum circuit, and then my PD, or my evolution system, I'm going to discretize it, meaning that every single time I'm going to do an Euler step to compute the new parameters in terms of the previous ones. And at each step, you need to solve to compute some matrices there. I'm not going to enter into any details there, but these matrices, we actually have some quantum circuit to compute them explicitly, or to compute them accurately. So this is what I wrote here, which is you start at time 0, you compute your optimal parameters. Once you have your optimal parameters, you can compute these matrices A and C, and once you have them, you apply your Euler step, which theta is just run as theta tau plus a short time step like this, right? So this is just an Euler step, and you go until maturity, and you test it. So what we did, I'll just have one more minute and I'll wrap it up. So we did that for European call option in Black-Scholes. I'm not going to go into detail, where we used 4 qubits. We could do with more, but we started with 4. And it actually, that was our first attempt, and it actually works pretty well. Pretty well, meaning that we are able to recover the classical solution. We're still working on theoretical results for to prove convergence, to prove accuracy. We're now working on trying to extend that to higher dimensions, so when you have more assets, for example, and how to build the quantum circuits that are needed in an optimal way. The last thing I want to mention in 10 seconds is people in quantitative finance have very little knowledge from quantum computing, so I think we need more interdisciplinary works in communication. And this is a tiny bit of advertising. There are 2 leading journals in the field, Quant Finance and SCIAM. I'm mentioning those 2 because I'm actually on the board of those, where we are open to computational aspects and new fields, So if you, we are open to new papers in that area if you look for new outputs. And I will stop here. Thank you very much.
Thank you very much, Antoine, for your talk. And now we have time for one question, which we have here from Renato. So the question says, in order to avoid the neural network intrinsic issues, can one write the time series forecasting problem as a supervised learning problem and use a kernel method instead of a neural network?
So, so I'm not sure. So neural network for what? For which part exactly? Can I actually see the?
Yeah, Renato, if you could elaborate, please, we appreciate it. Well, meanwhile, there's another question here by Renato himself, who says, since it is known that the Black-Scholes model systematically underprices options, are there alternatives?
Yes, of course. So the reason why I use Black-Scholes, so I wouldn't say Black-Scholes underestimate. It's not an underestimate. It's not a good model to price options because markets are different. But it's a standard model that we use for some computations. What is actually important is, in fact, you can see there's a little t that's in red. In Black-Scholes, sigma is constant. In reality, sigma is not constant. Sigma is also stochastic. So there are a certain loads of models which are a lot more involved, where sigma, the volatility, is also stochastic, where you can, either you can do PDEs as well, or you do Monte Carlo. But yes, I only focused here on Black-Scholes because it's the standard model, and basically, if things don't work with Black-Scholes, it won't work with anything. This is kind of the first, you could call it, baby step in a way to try on something. But of course, from the modeling side, this is a baby example.
Okay, well, thank you very much. Well, Antoine, we would like to say thank you for your presentation. Can you hear me?
Yes, yes.
Okay, thanks a lot. So thank you very much for your presentation. Time is over now. So thanks again and see you later.
My pleasure. Thank you very much.
Yes. Y ahora para los participantes, tenemos un break de 15 minutos. Podemos aprovechar yendo a los booths de las empresas, así como al área de networking. Now I'll say that in English too. We have now a 15 minutes break, so we can use it by going to the booths as well as to the networking areas in the same platform. Thank you very much. I'll see you here at 11:45. Nos vemos de regreso a las 10:45 AM, hora de Colombia. Gracias.
Thank you very much.
Cheers.